Have you ever really thought about what happens when you pluck a guitar string? Your one note, right? Well, it turns out that inside that single sound, there's this entire hidden universe of physics, this secret music. So today, let's dive in and uncover the beautiful complexity that's been hiding in plain sight this whole time.
So, that's the big question, isn't it? What is this hidden symphony? It seems like such a simple thing, a vibrating string, but the answer is what gives every single instrument its own unique voice. It's why music hits us the way it does. We're going to break it all down.
All right, first up, the sound of the string itself. You know that initial twang? That's not just one thing. It's actually a really complex event, a whole wave of information hitting your ear. Think of it like a stack of different sounds all arriving at once. So at the most basic level, this is what's going on. You give the string a little burst of energy, and it just starts oscillating, right? Back and forth along its whole length, this big, wide vibration. That's the most powerful part of the sound. It is the absolute foundation for everything else we're about to get into. And that big vibration brings us to something called the fundamental frequency. Now, if we think about a sound like a recipe, this is our main ingredient. It's the flour in the cake. It's the tomato in the sauce. It defines the whole dish, or in our case, the pitch of the note you hear.
So, what is it, technically? Well, the fundamental frequency is simply the lowest, and usually the loudest, frequency that an object, like our string, can produce when it vibrates. It's all about the string's length, how tight it is, and how thick it is. This guy is the king of the castle. The easiest way to think about it is this. If you were to hum the note you just heard from that string, you'd be humming the fundamental frequency. It's the note name we give the sound, like an A or a G. It's the most obvious, the most dominant part of what you hear. But, and this is a big but, it is definitely not the only part.
And this is where it starts to get really, really cool. Because riding on top of that main note are all these hidden layers of sound. And that brings us to the harmonics series. These are these perfect, almost mathematical layers of sound that are happening at the exact same time.
Okay, here's the part that might bend your brain a little. The string isn't just moving in that one big arc. Nope, it's so flexible and it's moving so fast that at the exact same time, it's also vibrating in halves and in thirds and in fourths and on and on. It's like it's doing a dozen different dances all at once. And this visualizes it perfectly. So look at step 1. There's our fundamental, that one big wave. Now look at step 2. At the same time, the string is also vibrating in 2 sections. This creates a note that's exactly double the frequency, a perfect octave higher. And then step 3, it's vibrating in 3 sections, and this just keeps going, creating this beautiful series of higher, fainter notes that are always perfect whole number multiples of the fundamental. It's just pure mathematical elegance in action. Okay, so we've got these perfect theoretical harmonics. But, the real world is never quite that clean, is it? And that brings us to a really important distinction, the difference between harmonics and overtones. This is where the perfect theory crashes into the messy, beautiful reality of a real instrument. And this slide just lays it out perfectly. Harmonics, that's the ideal, the perfect mathematical series, 2 times, 3 times, 4 times the fundamental, and so on. Overtones, that's what you actually hear from a real instrument. Now, for a guitar string, they're super close to being perfect harmonics. But for something like a bell, oh man, the overtones can be way more complex, not neat multiples at all. So here's the key. All harmonics are overtones, but not all overtones are harmonics. Now, I know this table can look a little tricky at first, but it really clears things up. See, the fundamental itself isn't an overtone, it's the main tone. So the very first frequency above the fundamental is what we call the first overtone, which just happens to be the second harmonic. Then the second overtone is the third harmonic, and so on. It's just a different numbering system, but it's really key if you want to understand how people talk about sound. So let's bring back our recipe analogy. If the fundamental is our main ingredient, what are the overtones? They're the spices. They are the paprika, the chili flakes, the oregano. They don't change what the dish is, but they give it its unique flavor, its character, its personality. And that idea, that flavor, brings us to our final section, an instrument's fingerprint. We can now use everything we just learned to answer one of the most basic questions in music. Why does a guitar playing a middle C sound completely different from a violin playing that exact same note? Well, the scientific word for this fingerprint is timbre, and it's pronounced timbre, kind of weird, I know.
Timbre is simply the quality of a sound. It's the richness, the color. It's the reason you can tell your best friend's voice apart from a stranger's, even if they're saying the exact same word at the exact same pitch. So, here it is, the whole shebang, the complete recipe for a sound. You start with your fundamental note, that's your bass. Then you mix in the specific overtones that instrument naturally produces. But here's the real secret sauce. It's all about the proportions. How loud is each of those overtones compared to the others? A violin might have a really loud third and fifth harmonic, while a flute might have softer ones. That final mix, that is what creates the unique timbre. That's everything.
And that just leaves us with one last thought to chew on. If every single sound we hear, a cello, a voice, a bird singing, is really just a recipe of different frequencies mixed together at different volumes, well, then what happens when we become the chefs? What other sounds can we build from scratch? This idea right here is the foundation of every synthesizer, of all modern sound design. It's an invitation to stop just being a listener and maybe start building.